Load balancing in Azure is crucial for distributing traffic across multiple backend resources, ensuring higher availability and optimal performance. Within the broader context of virtual networks, it plays a vital role in efficiently managing traffic flow, especially when dealing with critical applications. By directing requests to the least busy or most responsive resource, load balancing helps to mitigate bottlenecks and distribute workload effectively. When troubleshooting, it is essential to consider how subnets, virtual network peering, and security configurations might affect the distribution of traffic or the health probes used to determine instance availability. Understanding these underlying components benefits administrators by clarifying the path of the data and pinpointing any potential issues. In earlier discussions, we examined how name resolution, NSGs, and routing practices can affect reliability. Building on this foundation, troubleshooting load balancing starts with ensuring the entire network is structured and configured properly, allowing each component to collaborate without errors or misconfiguration. When load balancing malfunctions, certain symptoms often reveal the underlying root cause. For instance, an application might display frequent timeouts or slow responses, especially under high traffic volumes. These indicators could suggest that the load balancer is not distributing requests evenly or that some backend instances are unhealthy. Another symptom could be uneven utilization among backend virtual machines or instances, suggesting the health probes are failing or misconfigured. Additionally, unexpected traffic patterns, such as requests always routing to a single instance, might denote session persistence issues or incorrect port mappings. A thorough examination of performance data, including throughput metrics and connection logs, helps pinpoint these patterns. In many cases, configuration oversights in route tables or network security groups can hinder traffic, causing partial connectivity. By systematically analyzing these recognizable warning signs, administrators can expedite the troubleshooting process and restore balanced traffic distribution in Azure environments. Ensuring the accuracy of the backend pool configuration is one of the first steps in troubleshooting load balancing. A misconfigured backend pool can cause critical failures, such as directing traffic to inactive or non-existent virtual machines. Administrators need to check if the pool references the correct virtual network interface cards, NICs, and whether each NIC is associated with the proper subnet. It is also essential to confirm that the VMs are reachable and are not halted or deallocated. Utilizing Azure CLI or PowerShell commands to list and verify the pool members often reveals configuration mismatches. In scenarios involving multiple subnet or cross-region designs, verifying that each pool member adheres to the recommended guidelines prevents connectivity disruptions. For additional insight, administrators can incorporate diagnostic logs or logs from the Azure Network Watcher to confirm the association of correct network interfaces. By validating these configurations, troubleshooting efforts become more efficient and precise. Health probes are pivotal for any Azure load balancing scenario, as they determine the operational status of backend instances. Each probe checks availability at configured intervals, typically by sending TCP or HTTP requests. If these checks fail consecutively, the load balancer stops routing new connections to that instance. Analyzing health probe configurations involves reviewing probe settings like port, protocol, and interval frequency to ensure they align with the application's requirements. Moreover, verifying that the targeted port is open on the backend VM firewall is often essential, since a mismatch can result in a failing probe. Azure Load Balancer may also exhibit changes in probe behavior if NSG rules or custom routing disrupt the expected traffic. Logging tools, including Azure Monitor and Network Watcher, capture statuses for each probe and can highlight error codes. By examining these details, administrators gain clarity on why certain instances remain out of rotation, prompting a targeted resolution. Network Address Translation NAT rules in Azure Load Balancer facilitate inbound connections to specific backend instances, a mechanism vital for scenarios such as remote administration. When troubleshooting these rules, Administrators should validate that the mapped ports conform precisely to the load balancer's front-end configuration. A common pitfall arises when an NSG inadvertently blocks inbound traffic, preventing NAT rules from functioning correctly. Inspecting the effective security rules at the subnet or NC level can confirm whether legitimate traffic is allowed. Additionally, ensuring that the chosen backend instance is actively running the service on the correct port helps avert misrouted data. Administrators can reference Azure diagnostic logs to see if inbound requests are indeed reaching the load balancer and to assess whether they are properly forwarded to the target VM. By confirming these configurations and evaluating any potential IP-based restrictions, inbound NAT rule issues can be easily identified and resolved. Session persistence, sometimes referred to as sticky sessions, dictates how the load balancer assigns new client connections to backend instances over time. When troubleshooting, pinpoint issues by first checking which mode has been selected. For example, none, client IP, or client IP and protocol. If a specific persistence mode is enabled, requests from the same client should route to the same backend instance within a given time frame. Monitoring traffic behavior can uncover whether some clients are failing to sustain long-lived sessions. Misconfiguration of session persistence can cause random disconnections or break application states if the session context is not transferred across instances. Moreover, it is essential to verify the session configurations within the application itself, ensuring that session data is not forcibly reset by other network or security policies. By accurately configuring persistence settings and verifying the actual distribution of client requests, administrators can maintain consistent performance under a variety of workloads. Troubleshooting load balancing also involves understanding the flow of traffic and how requests are routed. Unusual traffic distribution might indicate a misaligned load distribution policy, where round-robin is set instead of the desired performance-based or IP hash-based approach. Administrators can observe traffic patterns using Azure Monitor logs, checking for anomalies like a single VM receiving a disproportionate fraction of the overall load. In addition, potential issues may arise from application layer protocols that embed client IP references, leading to uneven routing if advanced load balancing configurations are incomplete. Capturing and analyzing flows using Network Watcher helps confirm whether the traffic is being correctly forwarded at each network hop. If cross-region or geographic load balancing is involved, verifying that traffic is being routed to the intended region can reveal possible misconfigurations. Through careful inspection of logs and monitoring tools, administrators can gain valuable insight into distribution problems and act accordingly. Layer 4 load balancing in Azure relies heavily on properly defined forwarding rules. These rules specify how incoming requests map to destination backend ports and protocols. In troubleshooting scenarios, verifying that the load balancer front-end IP and port align with the intended listener configuration is a crucial first step. Pertinent checks include confirming that the protocol, TCP or UDP, matches the service requirements and that the backend port is properly targeted. Additionally, forwardings can fail if an associated health probe is not well established, causing the load balancer to mark the instance as unhealthy. Administrators often leverage Azure CLI or PowerShell to retrieve the configuration details on each load balancing rule, ensuring that the correct backend pool and port are referenced. By methodically reviewing the association between front-end and back-end settings, as well as ensuring that no conflicting route or NSG rule obstructs traffic flow, many load balancing issues can be promptly resolved. In Azure, security mechanisms such as NSGs, application security groups, ASGs, and custom routes influence the overall functionality of load balancers. When investigating connectivity issues, administrators should confirm that inbound and outbound rules permit relevant ports and protocols. NSGs that are too restrictive can inadvertently block health probes or inbound connections from clients. For instance, if a load balancer health probe uses port 80, any conflicting deny rule within the NSG might prevent the probe from reaching the VM, resulting in a perceived unhealthy instance. Similarly, User-defined routes that redirect traffic to a specific appliance or region might interfere with intended load balancing paths. By systematically reviewing effective security rules, particularly those applied at both subnet and NIC levels, administrators can detect potential conflicts. Documenting each rule and its priority can highlight misconfigurations. This practice is especially beneficial when diagnosing complex multi-tier architectures where firewall rules or custom appliances play a critical role. Azure provides an array of logging and diagnostic tools to assist in pinpointing load balancing difficulties. Network Watcher is a key component that enables packet captures, facilitates connection troubleshooting, and inspects next-hop behaviors. Administrators can configure network security group flow logs to examine the ingress and egress traffic at varying stages of the data flow. Additionally, Azure Monitor aggregates metrics such as CPU utilization, data path availability, and the status of the health probes, assisting in trend analysis. Logging can be extended through Azure Log Analytics workspaces, enabling custom queries that visualize traffic patterns and highlight abnormal behaviors. Such insights become vital when investigating sporadic connectivity drops, as the logs capture precise timestamps and network paths. By combining these tools, particularly with application insights for deeper application-level monitoring, teams gain a multifaceted perspective on the environment. This detailed visibility aids in formulating prompt and targeted resolutions to load balancing issues. Metrics serve as quantifiable indicators that can streamline the resolution process for load balancing malfunctions. Azure Load Balancer publishes metrics for data path availability, number of allocated SNAT ports, and the overall volume of inbound and outbound flows, among others. Administrators often rely on graphs and alerts to identify deviations from normal operating conditions, such as a sudden spike in back-end response times. By analyzing these metrics over a historical timeline, anomalies linked to interface saturation, session exhaustion, or misconfigured probes can be correlated with specific events or deployments. Metrics can also expose underutilized resources that may inadvertently skew load distribution. Implementing automated alerts allows administrators to respond quickly to problems before they escalate. In large-scale environments, metric-based diagnostics complement standard log-based troubleshooting, providing early warning signals of network or performance degradation. Properly interpreting these metrics fosters a proactive approach, minimizing downtime related to load balancing disruptions. Command line interfaces, such as Azure CLI and PowerShell, are indispensable for administrators needing granular insights into load balancer configurations. With a few commands, one can list health probes, examine front-end and back-end pool associations, or retrieve load balancer rules. For example, with Azure CLI, administrators might run AZ Network LB list to retrieve a list of existing load balancers, followed by AZ Network LB show to inspect a specific resource in detail. PowerShell equivalents, such as get AZ load balancer, serve a similar function. Such commands enable quick checks for missing or misaligned parameters that might be challenging to identify through the portal alone. Furthermore, scripts can be automated to run routine validations, ensuring load balancer settings align with predefined best practices. When investigating issues in complex deployments, command line queries expedite the discovery of potential discrepancies and help isolate the root cause. By leveraging these utilities, administrators can streamline the troubleshooting process across Azure environments. DNS resolution and routing directly influence how client requests reach the load balancer's front-end address and whether responses return appropriately. When problems arise, administrators can confirm that DNS records reference the correct public or internal load balancer IP address. In complex network scenarios, user-defined routes or forced tunneling might inadvertently redirect traffic in unintended ways, leading to unresponsive services. Checking route tables at both the subnet and NIC levels can reveal if the load balancer traffic is being dropped or rerouted. Tools like AZ Network NIC's show effective route table provide clarity on final routes, while Azure DNS logs reveal potential misconfigurations or domain mismatches. Additionally, multi-region architectures sometimes involve separate DNS entries or advanced traffic management to direct requests to the nearest load balancer resource. Ensuring that these entries align with the Azure load balancer's location and front-end configuration helps maintain stable connectivity. By systematically examining these DNS and routing elements, troubleshooting becomes more focused and methodical. A thorough review of typical root causes can streamline the troubleshooting process for Azure load balancing. Some of the most common pitfalls include misaligned NSG rules, incorrect or missing health pro configurations, and mismatched front-end/back-end port definitions. Additionally, session persistence settings that fail to align with application requirements can trigger random disconnections. Another frequent issue arises from ephemeral SNAT ports becoming exhausted under heavy load, particularly if multiple back-end applications compete for limited outbound connections. Drawing on logs, metrics, and DNS records helps to pinpoint whether these factors contribute to the disturbance. Administrators can reference the table below to clarify typical causes and suggested approaches. Issue approach. Health probe failures check port, firewall, NSG settings misconfigured NAT rules verify, front-end ports and target session persistence errors align mode with app requirements by focusing on these recognized areas. Teams can accelerate diagnosis and minimize potential downtime.